Alright. I'm going to show, that should be inverse without a space. I will fix that. I'm going to show that the inverse is also going to be, the inverse of a linear transformation is also a linear transformation. So let T going from some linear space V to W be a linear transformation with inverse. Let's just use S for now. So what does that mean? That means that S of T of V equals V for all V belong to V, and Ts of W equals W for all W belong to W. I'm going to prove that S is linear. And I'm going to do that by letting, how about W and X belong to W, and how about K be a scalar? So what am I going to do? I'm going to show that S of W plus X equals S of W plus S of X. I'm going to show that S of K times W equals K times S of W. But I just need to set some things up first. Also, I'm going to suppose, what do I need? But A, B, C, and D belong to V with T of A equals W, T of B equals X, T of C equals W plus X, and T of D will equal KW. So I only really know about S in terms of T. So by the way, very, very briefly, this sort of thing means that S of W equals A by the way we define S. Similarly, S of X is going to equal B, S of W plus X is going to equal C, so on and so forth. So I'm going to consider S of W plus X. And I'm going to want to show that this is equal to S of W plus S of X. And I know that this is equal to C by this definition right here. So what do I know? I can apply T to both sides of this. T of C. But T and S together just allow me to write down like so. This is equal to T of C. By the way, I'm trying to translate everything in terms of T's, because I know that T is linear, and so that's something that's really nice. I also know that how should I write this? Maybe I'll write it this way. W is equal to T of A. X is equal to T of B. So, and this is equal to T of A plus B by the linearity of T. So T of A plus B is equal to T of C. T of A plus B is equal to T of C. Now, what I just showed you not too long ago was that T is invertible if and only if it's 1-to-1 and onto. So, since T is invertible, T is 1-to-1. I don't really care about onto right now. So that means that A plus B equals C. Right? That's what 1-to-1 gives you, is that if you ever have two outputs the same, the output T of C is equal to the output T of A plus B. That means the inputs were the same. That's what 1-to-1 means. But let's see. We're almost here now. So what I can do is think about this for a second. So T of C is equal to, how'd that happen? I'm just going to scroll this in a little bit. There you go. So what I can do is I can take T of both sides once again. Let me get my thoughts here. Oh, so yeah, now I can just apply the definitions. What is A? A is equal to S of W by this relationship right here. And similarly, this means that S of X is equal to B. So I can replace this with S of X. And C means that S of W plus X works like so. So this is the first equation of linearity. And now I just need to consider, by a very similar game, S of KW, which equals D by this equation right here. I'm also going to consider, how about K times S of W, which equals K times A. So I can apply T to both sides here. That gives me KW here is equal to T of D. What's T of D? It's equal to KW. How about that? Let's see. So what does that buy me? Actually, you know what? I can do this a lot more simply. So let's just do this. I'm going to use the fact that there I am. I can use the fact that T of D equals K times W, which equals K times, what's W equal to? W is equal to T of A, which equals to T of Ka by linearity of T. So what I can do is I can take S of both sides equals S of T of Ka. So I get that D is equal to Ka. But what is D equal to? D is equal to S of Kw. Why is that? Because T of D is equal to Kw. What's K times A equal to? Well, it's equal to K times A. Well, what is A? A is equal to S of W. So this is the second part. So in other words, S of Kw is equal to K S of W. So since these two things both hold, we should see that S is linear, which means that the inverse is also linear, since S is inverse. That's it. We're done.